Okay. So, review. For any random phenomenon, each trial, can you see that on the screen behind me? Okay. Each trial generated an outcome, an event is any set or collection of outcomes. The collection of all possible outcomes is called the sample space, or S. So, for example, if a family has 2 children, okay, the sample space, now think about this, the sample space is BB, BG, GB, or GG. What am I talking about there? Am I speaking gibberish? Combinations of boys and girls. Now, why is BG different from GB? Order matters, right? It does matter. Does order matter in birth? Or okay, because here the boy is older, here the girl is older. Okay, so they are different. So in this case, all 4 outcomes are equally likely. Okay, because the chance of being a boy or a girl on each birth is what? 50%. Okay. So now, if you are dealt 5 cards from a deck and record the number of aces you get, what is the sample space? So think about, I'm recording the number of aces. That is the different possible things that can be is the sample space. So the sample space S would be what group of numbers? How many aces can I get? I could get 4. What else could I get? I could get 0, 1, 2, and 3. Are there any other possible outcomes for the number of aces in a deck of in a hand of 5 cards? Could I get 5? Can I get 5 aces? No, you can't. A deck of cards has 4 aces. Okay? Do any of you not know about a deck of cards? A deck of cards has how many cards?
52.
52 cards in a deck. Okay, there are 4 suits. The suits are hearts, spades, upside down heart with a stem, clubs, and diamonds. Okay, so there are 52 cards in a deck. There are 4 suits. There are 13 cards in each suit. Okay, and the cards go from ace up to king. So basically ace through 10 and then jack, queen, king. It depends on the card game you're playing. Ace can be the high card or the low card. Okay, so that's just the makeup of a deck of cards. So there are 4 suits, there's 4 of each card, referring to the 4 aces, 4 tens, 4 jacks, 4 queens, 1 of each suit. All right, so when all of the outcomes in a sample space are equally likely, the probability of an event A is, here's the probability, I went through this in the video too, it's in your book too, the probability of an event A. We were writing probability problems like the probability that 1 car needs repairs. A just refers to any event. The count of outcomes in A divided by the count of all possible outcomes. We did that when we were doing the trials on the board. Okay, we were doing simulations. So, for example, the probability that a family with 2 children has 2 boys is 1/4. Okay, the probability that a family with 2 children has 2 boys is 1/4. Now, where did that come from? Well, up here, isn't that the total sample space for the 2 kids?
Yep.
That would be the bottom number. 4 would be the bottom number. And how many of those have 2 boys? 1 of them. A, the event A, having 2 boys, has 1 of those 4 outcomes. Has 2 boys, the total is 4. Now, but on the other hand, the probability of getting 4 aces in 5 cards is not 1 out of 5. You can't say, well, there's 5 outcomes for the number of aces you get, and 1 of them has 4 aces, so this is not 1 in 5. because the probability of getting 4 aces is a lot smaller than the probability of getting no aces, right? It's not very likely when you have a 52 card, you have 52 cards in your hand. I'm only giving you 5 of them. Okay? The chances of you getting 4 aces are a lot smaller than getting no aces. So the probability of getting each of these is not equally likely here, because we're actually pulling from a bigger pot than just 4 aces. All right, so what is the probability of drawing a single card from a deck and getting a red card or an ace? Okay. The probability of drawing a single card from a deck. So I'm going to draw a single card. This is important. Whenever you draw a single card, it's usually a whole lot easier than if you draw multiple cards. Okay? Drawing a single card is really easy. Drawing multiple cards is harder. Just like in the problems that we just had on our homework, if we only have 1 card needing repair, it's easy. As soon as you have 2 cards that need repairs, the probability becomes slightly more complicated. Okay? Then we have to deal with and ors combined together. So if I'm just going to draw a single card, the probability of getting a red, so the probability of getting a red or an ace. Notice how I take the words and I write it as a probability problem. Okay? If I can't write it as an or an and problem right away, that's okay. I try to figure out which it is, but here it was just, it had or already. So that's the same as the probability of getting a red card plus the probability of getting an ace. So what's the probability of getting a red card out of a deck of cards? Well, how many total cards are in the deck?
2.
And how many are going to be red?
26.
26. Half the cards are red, half the cards are black. So 26 out of 52. I'll reduce that later. Don't worry about it. Plus, what's the probability of getting an ace? Well, out of the 52 cards, how many are aces? 4. Okay? So, well, let's see. I'm going to draw a little picture of this, because you might think we're done and we're right. Okay? Probability that I pick a red or an ace. Now, this or probability that I gave you in the last set of notes was if the events were what?
Independent.
Not independent. Somebody said the right word. Disjoint, okay? This works for disjoint events. So what did I say? How do you decide if things are disjoint?
Not doing it.
Very good. If you can't be both, you can't be both. Disjoint events, you can't be both or do both at the same time. So I always ask myself, here's the 2 things. Can I be a red ace? Can I be red and an ace? Okay. So this is not the right probability here. Okay. Because what happens, these are not disjoint events here. You can be a red ace. Okay. In fact, how many red aces are there in the deck? 2. So I have a question. Didn't we count those 2 red aces here? Weren't both red aces in these 26 cards that were red? Weren't both the red aces also here? So we counted those red aces twice. So in order to make this probability correct, we have to subtract the 2 aces that I counted twice. Sometimes things called, have you ever heard of a Venn diagram?
Mm-hmm.
Okay, so here you've got red, and then you've got aces. Well, they overlap. Okay, they overlap by 2 cards. These are if you can draw a Venn diagram and they'll overlap, both of the groups will overlap, they're not disjoint. So then this or probability no longer works as easily as we want it to. So to find the right probability, we had to subtract this. Subtract what we added twice. So this the correct probability for the probability of getting a red or an ace, well, 26 plus 4 is what? Minus 2. So 28 out of 52, which you could reduce, or you could just change it to a decimal. What is it, Alexis?
0.538.
0.538. Okay. Sometimes it's easiest just changing it to decimals. All right, so now we answered this problem, so I'm going to reiterate what we just did. Okay, I'm just reiterating what we just did, and I'm going to write it in what's called the general addition rule. So down here is going to be a rule that's important. So to answer this problem, we need to use the general addition rule. Okay, this is a rule that's in your books, which works when events are disjoint and when they're not disjoint. So your normal, the OR probability formula I taught you before, throw it out. This is the one you use all the time now. So the probability of event A or B happening, which is the same as the probability of event A union event B, just sit in the back, it'll be a while. This little U, if you watch the videos, means union. It's the same as an OR. It comes from set theory classes that you can take, discrete math classes. So that's the probability that event A happens, plus the probability that event B happens. But then here's the new thing to the rule. You have to subtract the probability of event A and B happening. So again, the probability that I got a red or an ace was the probability that I got a red plus the probability that I got an ace minus the probability that I got, well, a red and an ace means I got a red ace, right? The last probability, the one we took off, was the probability that you were both red and an ace. So the probability that you were red was 26 out of 52. The probability that you were an ace, well, that's 4 out of 52. And what's the probability that you were a red ace? 2 over 52. So this is the general addition rule for finding OR probabilities, whether the events are independent or, disjoint or not disjoint. So when we use the word OR, we mean it in the inclusive sense. A or means B. A or B means A occurs or B occurs or both A and B occur. That's what the or means in the inclusive sense. So let's take a look at this example down here. Suppose that 75% of students in statistics are seniors. Okay, 90% have a TI-83 and 70% are seniors with the TI-83. Okay, this is a question we had before. We're just revisiting the same question. Now we have the more information. So it says, what is the probability that a randomly selected statistics student is a senior or has a TI, a graphing calculator? So now, knowing the general addition rule, that would be the probability that you're a senior plus the probability that you have a TI minus the probability that you are a senior with the TI. Senior and you have a calculator. Because you can be a senior that has a calculator, right? You can be a senior and have a calculator, correct? Or are seniors not allowed to have calculators?
No.
Okay. All right, so the probability that you're a senior is what? 0.75 plus the probability that you have a TI, 90, minus what's the probability that you are a senior and have a TI? 0.7. So now if we add these two probabilities, we get 1.65 minus 0.7, we end up with 0.95. And is that a valid probability? The last time we did this, we didn't have this piece of information about the 70% having both, being a senior and having a TI.